Hey, so this is Joe, and this is the fourth video in the 14th chapter of Stewart's Calculus. We're going to be talking about the chain rule applied to three or more dimensional functions. So, first we start off with our total differential formula that we talked about in the last video. So we have dz is equal to the partial derivative of z with respect to x times the x differential plus the partial derivative of z with respect to y times the y differential. So this brings us to our total differential version of the chain rule. And the total differential version of the chain rule is if we have some function in terms of x and y, or more variables, equal to some variable z, and so we have a function like that, and we can express x as a function of one parameter and y as a function of that same parameter. And when we have these three conditions met, then we use our total differential version of the chain rule, which basically looks exactly like our differential our total differential definition here, except everything is just divided by the time differential, and that's the time total differential. So you see we've got dz dt, so that's the rate of change of z, as opposed to just the differential of z right there, and that is going to be equal to the partial derivative of z with respect to x times the derivative of x with respect to t times the partial derivative of z with respect to y times the derivative of y with respect to t. And when we use these total derivatives right here because we parametrize both these variables x and y using one variable, the same parameter. And so this is the first version of the multivariable chain rule. That's useful for a lot of applications. However, we have a more general version of this chain rule that applies to functions in more than two variables and which are parametrized by two or more variables. So let's take a look at that right here. So here's our partial differential version of the chain rule, and it says, and so because it's the partial differential version, that means that there are two possible variables with respect to which we can take the partial derivative of z. So that means that we have some equation z that's equal to some function of x and y, or more different variables, but that means that x is parametrized as a function of two or more parameters. In this case we can call them s and t, and y is parametrized with respect to those same two or more variables. And the more variables that are your parameters, the more possible partial differentials you can partial derivatives you can find, and the more variables in your function that corresponds to z, the more terms you're going to have in each of these that correspond to each of these partial derivatives. So basically, we have the same chain rule. It's the exact same for each partial derivative. You're trying to find z with respect to some parameter, and that's going to be equal to z, the partial derivative of z with respect to one of the intermediate variables, either x or y, times the derivative of that variable with respect to the parameter. However, the derivative of the variable with respect to the parameter and the derivative of the function that you're trying to find with respect to the variable or parameter, those are partial derivatives because you can take the derivative of that variable or that function with respect to multiple parameters. And that's why we have these two options here. We have the partial derivative of z with respect to s, and with respect to t. So really the only difference between the partial differential version of the chain rule and the total differential version of the chain rule is the number of parameters that you're using to describe each of the intermediate variables x and y at hand. And so that leads to a number of different possible partial derivatives you can get out of that. So that's kind of it theoretically for describing the chain rule in multiple variables. Now we're going to do two problems, that one of which will involve the partial differential version and the other of which will involve the total differential version. So let's take a look at those. We're going to do number 9 on page 954 in your book, and we're given oh, I copied this function down wrong. We're given a function z equals sine theta times cosine phi is written like that, and we're parametrizing theta as a function of two parameters. Precisely, it'll be s times t squared, and phi is parametrized by the same two variables, parameters I should say, and that is going to be s squared t. So what we're asked to find, and so this is going to, already we know that since the two intermediate variables, theta and phi, are parametrized by the same two parameters, that means we're going to be using the partial differential version of the chain rule. So the question asks us to find the partial derivative of z with respect to s and the partial derivative of z with respect to t. So first let's start off with the one with respect to s. So we'll get our little rule out. We'll write the chain rule out explicitly. We'll have dz, del z, del s, and that's going to be equal to del z, del theta times del theta, del s, plus del z, del phi times del phi, del s. So all we need to do is find each of these, and eventually we'll have to end up plugging in for theta and for phi. So first, del z, del theta. We look up here at our equation, and we can treat the cosine phi as a constant, and the derivative of sine theta is going to be cosine theta. So it's going to be cosine theta, cosine phi, and then the derivative of theta with respect to s, we treat the t squared as a constant, and that's all we're going to get out of that. We're going to get a t squared, like that. And now we come over and we take the partial derivative of z with respect to phi. So that means our sine theta is going to be that's going to be a constant. The derivative of cosine phi is going to be negative sine phi. I've already got our little negative out there. So it's going to be sine theta, sine phi. And now we have to take the partial derivative of phi with respect to s. And so that means this t is going to be a constant, and we'll get a 2st. And so we come down here, and we'll plug in for theta and for phi. And so then we will get the partial derivative of z with respect to s, like that. Now we're going to go up and we're going to find the partial derivative of z with respect to the other parameter, t. Alright, so now we've got the partial differential form of the chain rule written out here, and we're trying to find del z, del t. And so first off, we're going to have to find del z, del theta, so the partial derivative of z with respect to theta. So that means we treat this cosine phi as a constant, and we'll take the derivative of sine theta. Oh, and so that means we are going to get cosine theta, cosine phi, and so we'll take now the derivative, or the partial derivative of theta with respect to t. So we're going to treat this s as a constant, and so we'll get 2st, like that. And now we'll find the partial derivative of z with respect to phi. So we're going to treat the sine theta as a constant, and this positive right here is going to become a negative, and we are going to get sine theta, or negative sine theta, sine phi, and we're going to find the partial derivative of phi with respect to t, and so that will give us, we're going to treat this s squared as a constant, and we're just going to get an s squared, like that. And so now we can plug in these expressions of s and t for our intermediate variables, theta and phi, and that'll look like this. That is the partial differential form, or partial derivative, I should say, of z with respect to t. And that's kind of all she wrote for the partial differential form of the chain rule. Now let's look at one more problem that will involve the total differential form of the chain rule. In other words, we're parametrizing the two intermediate variables with only one parameter. Alright, so now we're going to do number 40 on page 955, and I've kind of written out a lot of the information here given to you in the problem for you. But basically we're dealing with what's called in physics, or the or E&M side of physics, Ohm's law, that relates current, resistance, and voltage with V equals I times R. And what we're trying to do is we know that the resistance and the voltage are changing, and we know how much they're changing. Voltage is decreasing as resistance increases, and so the rate of change of voltage with respect to time, so dV dt, is negative 0.01. and the derivative, or the rate of change of the resistance, or dr dt, is equal to 0.03. And so what we're asked to find is we're asked to find the rate of change of the current, or di dt, and we're asked to find that when resistance is 400 and the current is 0.08. So first off, the fact that we're given, and so we can rearrange this equation v equals IR however we want. We could make I a function of R and V, we could make R a function of V and I, we could make V a function of I and R. However, we're told that we should make V a function of I and R because we are given values of both R and I, so we know that those are our two intermediate variables. Also, we have one, we know we have that both of these variables are parametrized by one parameter because we're trying to find the rate of change of everything with respect to time, because we're giving these time derivatives. So that means we're going to have to use our total differential form of the chain rule. So because v is a function of I and R, we have dv dt is going to be equal to dv del v del I times di dt plus del v del r times dr dt. So right now we can plug in for what we know. dv dt, we have a value for that. That's negative 0.01. Del v del I, we don't know yet. di dt, that's what we're looking for, so we're going to keep that here because we're trying to find out how the current changes when voltage and resistance are changing like that. Plus, and then del v del r, we don't know that yet, but we can calculate it because we have a function of I and R expressed as v. And dr dt, we have a value of that. That's 0.03. So now we have to do our partial differentiation here. So del v del I, the partial derivative of v with respect to I, so that means we treat r as a constant and I as our variable, so that del v del I is going to be r, and we're trying to find that, remember we're trying to find del v del I and del v del r when r is 400 and I is 0.08. So now we have r times di dt plus, and now del v del r, we treat r as our variable, I as our constant, and we're going to get an I 0.03, and this is all equal to negative 0.1. So what we need to do now is plug in for r and I. So we'll get negative 0.01. R is 400 times di dt plus, and now I is 0.08 and times 0.03, and we can rearrange all of our variables and we will get that the rate of change of the current with respect to time is going to be negative 3.1 times 10 to the negative fifth. So basically we understand that the current is going to be decreasing, but decreasing very, very, very slowly. So that's it for the chain rule multivariable style. Stay tuned for the rest of the chapter, and I hope this was helpful. Thanks.